Okay, so today we'll continue with the single object allocation problem. Can everyone see the screen?
Yes, sir.
Yes, sir.
Okay.
Yeah.
Okay. So just to recap, last time we finished the characterization of dominant strategy incentive compatible mechanisms for single object allocation problem. So the following theorem was proved that if we have a tight space which is a product of these closed intervals for each of the agents, then a mechanism FP is a DSIC if and only if F is non-decreasing, and for every I and every T minus I, this payoff formula holds. Okay, and we saw some consequences of this characterization. In particular, we showed that following the so-called revenue equivalence implication of that if you have two mechanisms, FP and FP prime, that is both the mechanisms use the same allocation rule, but their payments are potentially different and they are both DSIC, then the payments are different at the lowest type, and this difference is translated across all types. Okay, so the difference at Ti is the same as the difference at Z. Okay, and this is what is called the revenue equivalence principle or formula, that two mechanisms using the same allocation rule must differ in payments only at the only due to the difference in payment at the lowest time. Okay, so in particular, if you have the lowest type payments to be the same, then the two mechanisms must be the same too. Okay? And so the main takeaways from those lectures is that a DSIC mechanism can be thought of as a non-decreasing allocation rule and a payment rule which is uniquely determined by the payment at the lowest type and this integral formula which involves the payment at the lowest type and the allocation rule. So hence, if we fix the payment at the lowest type and the non-decreasing allocation rule, we fix the entire payment. That's the main takeaway from this, and we are going to use it in various ways in coming lectures and today also. One of the things we discussed was how that characterization simplifies. This particular characterization simplifies if we have F to be deterministic. So F is either 0 or 1 at every type profile. So every agent gets the object or doesn't get the object, so there is no randomization involved. So for those kind of allocation rules, for deterministic mechanisms, the non-decreasingness essentially implies a cutoff allocation rule, which means that for every agent and for every T minus I, there is a cutoff point above which the agent starts winning the object. And the cutoff point essentially determines the payment the agent makes if he wins the object. So in particular, we showed that if F is deterministic, then FP is DSI if and only if F is a cutoff allocation rule. And for every I and every T minus I, the payment of the loser is just Pi 0 T minus I, the payment he will make at the lowest possible time. And the payment of the winner is Pi 0 T minus I plus this cutoff amount, which is the least amount needed for the agent to start winning the object. So the least time at which the agent starts winning the object. Okay. So the simplest illustration of this is when Pi 0 T minus I is equal to 0. In that case, the payment of the loser is either 0, the payment of the loser is 0, and the payment of the winner is the cutoff point. Okay, so that's where we were last time. And what I'm going to do today is to move to some other constraints besides incentive compatibility. And in particular, I'm going to talk about participation constraints. So this is the first, notion of participation constraint. and this is called ex post individual rationality. So as the term suggests, that we are going to require a very strong form of participation, meaning that exposed, once the mechanism is finished and the agents are done with the mechanism, they don't regret participating in the mechanism. Okay, so what does that mean? That the definition says that a mechanism FP is exposed individually rational if for every I and every type profile T, the utility of the agent at this type profile is greater than equal to 0. So Ti Fi Tit minus I minus Pi Tit minus I is greater than equal to 0. So what this assumes is that the outside option of the agents is to not get the object and not pay anything. So that is the outside option is 0, and hence if the incentive, the participation constraint requires that the utility that they get must be greater than equal to 0. Of course, there are many settings that we will study later where the outside option need not be 0. So we will have it in the model that what the outside option would be. Uh, if an agent decides not to participate. Okay, so in that case, this participation constraint will change. But for the moment, I'm going to assume that the outside options utility is normalized to 0, and hence the participation constraint just says that the exposed utility of every agent is greater than equal to 0.
Sir, in this setting, what will be the ex ante individual rationality condition?
Yeah, so the ex ante is basically the for computing ex ante or interim terms, we will come to that. We will require some prior on the distribution of types and so on. So the ex ante or interim would say that the expected utility from participating in the mechanism is greater than equal to 0. So I'm making a decision about participating in the mechanism before I realize my type, and so my ex ante utility must be greater than equal to 0.
So here we are assuming that when he reports truthfully, he gets a non-negative utility, but by participating, he can report anything, not necessarily.
Yeah, so that's an important point. So basically, the participation constraint is always taken with the incentive constraint. So essentially what it means is that we are looking at a mechanism where truth telling is some kind of an equilibrium, and hence the net utility that you get is an equilibrium utility, and so it reflects the actual utility you will get in the mechanism.
Okay.
Okay. So participation constraint is always taken together with incentive constraints. Okay. Anything else? Okay. So of course, this is a very strong notion of individual rationality. We will, at the end of today's lecture, I'll also come to a weaker notions of individual rationality. Okay. So here is the characterization of exposed individual rationality. Suppose you have a DSIC mechanism. It is exposed individually rational if and only if for every I and every T minus I, Pi 0 T minus I is less than equal to 0. So all it requires is that lowest type is never asked to pay. Okay, he may be compensated, but he is never asked to pay. So if this condition is satisfied, then individual rationality holds at every type profile. Moreover, this condition is also necessary. Okay, and the proof is quite straightforward. So let's do one direction. Suppose we take a mechanism which satisfies ex post IR. So if ex post IR is satisfied, then basically, this UI 0 T. So if you apply the ex post IR constraint to the type 0, then the first term is 0. So we'll get minus pi 0 t minus I is greater than equal to 0. Hence pi 0 t minus I is less than equal to 0, which is exactly what we have here. Okay. So ex post IR implies this condition because this is just ex post IR constraint for ti equal to 0. Okay. Now the other direction follows because this is a DSIC mechanism. We know that for every ti, ui ti t minus I is equal to this particular term. ui 0 t minus I plus this. Okay. But this condition implies that ui 0 t minus I is greater than equal to 0, right? Because if pi 0 t minus I is equal to 0, then this has to be greater than equal to 0. But this term is always non-negative. So the entire thing is non-negative. So pi 0 t minus I less than equal to 0 also implies ui ti t minus I greater than equal to 0 for every ti. Okay. So this condition is both necessary and sufficient. Okay, so this is the simple proof of this. Any confusions? Okay. So of course, if you have, you should all look at these videos after the class is done. You should also look at the class notes just to clarify your doubts or anything on this. You can also ask me questions along the way, and you can also email me to have discussions. Okay. Anyway, so this is a simple observation that ex post IR is essentially a constraint on the payment at the lowest time. That's all. Okay, that the lowest type payment should be non-positive. Okay. Um, so of course, an immediate corollary of this is that if you have ex post IR and non-negative payment, right? Because ex post IR implies that pi 0 t minus I is less than equal to 0. But if you insist that payments are always non-negative, that you are never allowed to compensate any of the agents, then that would basically implies that pi 0 t minus I is equal to 0. Okay. So an immediate observation is that DSIC ex post IR and non-negative payment is completely pinned down by allocation rule. Okay, so any mechanism which is DSIC, ex post IR, and satisfies non-negative payment can be completely described by the allocation rule itself. That's because we have just shown that such a mechanism will satisfy pi 0 t minus I is equal to 0, right? And that means that in this characterization here, this term basically disappears. This is equal to 0 because pi 0 t minus I equal to 0 means ui 0 ti minus I is equal to 0. So that means that this characterization just requires that f is non-decreasing and ui ti minus I is equal to this integral which only depends on the allocation. So what we have basically shown is that any DSIC mechanism which satisfies ex post IR and non-negative payment can be completely described by a non-decreasing allocation.
How this observation is important?
This observation is important because remember, so suppose, we have no idea about the space of all DSIC mechanisms. So we start with FP, which satisfies DSIC incentive constraints. And then for some reason or the other, we start imposing other constraints, which is ex post IR and non-negative payment. For some reason, I'll come to what those reasons can be, but let's say we impose ex post IR and non-negative. But then immediately what we see is that we don't need to worry about P at all because P is completely determined by F now. So the space of our mechanisms is just the space of all non-decreasing allocation rules. So if I were to optimize over all FP, which is DSIC, and satisfies ex post IR and non-negative payment, it is equivalent to optimizing over the space of all non-decreasing allocation rules. That's why it's a reduction in the space of variables essentially. You don't need to worry about the space of P's in some sense. It's just in the space of F's now. So in some sense, it implies some kind of reduction in dimensionality of the problem. Okay.
Okay, sir.
We'll come to optimizations in the next class, and you'll clearly see these things in action when we do those optimizations. Okay, so that's so ex post IR and non-negative payment essentially means that pi 0 t minus I is equal to 0, and then we have this space of just non-decreasing allocation rules to worry about. Okay. This is just saying the same thing, that FP is DSIC ex post IR and satisfies non-negative payment if and only if F is non-decreasing and the utility function is completely determined by the F. Okay. So now for the rest of the lectures, I'm just going to give two main applications, two somewhat important examples or applications of this result. And both the applications are about redistribution mechanisms, and you know, in about 2 or 3 lectures, we'll get into details of redistribution mechanisms, but this is just a small warm up towards that. So let me just step back for a moment and try to tell you why redistribution is important. So of course we are studying single object allocation problems, but even inside the single object allocation problems, the designer may have various objectives in mind. So the common objective is efficiency, that the designer just cares about giving the object to the agent who has the highest value. Okay, so something like the Vickrey auction can do the job, but we know that there's a class of Groves mechanisms which can also do the job. And so that's one thing. But we can also be interested in revenue maximization, for instance. So we might be a seller who is just interested in maximizing revenue. It's not clear that when you want to maximize revenue, you want to give the object to the agent to the highest value. And as you will see in the next lecture, that indeed, if you want to maximize revenue, sometimes you should not be doing that. Okay, and it will be clear. And so these are two common objectives, but there is also an alternate view of allocation problems, which is this redistribution view. So what is the redistribution view? The basic point here is that think of a society which is trying to allocate some object, and basically the only purpose of allocating this object is basically by allocating the object, one of the agents will realize a value for the object, but somehow the objective is to redistribute the value gained by this agent amongst all the agents in the society. Okay, so this is what is called a utilitarian view of allocation. So when we allocate, for instance, when we think about Vickrey auction, for instance, we allocate the object to the agent who can get the maximum value from the object, but the agent pays something which is no longer distributed amongst the agents, right? So that payment that is raised by Vickrey auction goes back to the seller, and the other n minus 1 agents basically get zero utility. So the Vickrey auction is never meant for redistribution. If you cared about redistribution, essentially the value that the highest valued agent gets, there must be a way to redistribute that value amongst all the agents. And of course, this has to be done in an incentive compatible way. So if you said that, well, whatever revenue the seller is getting from the Vikri auction, why doesn't it equally distribute amongst all the other agents? Well, that's not going to work, because that may lead to some kind of manipulation. It may not be incentive compatible. So we need to be careful about the ways we should redistribute these, through these incentive compatible mechanisms. So what I'm going to tell you,
Sir, can we separate out this problem of redistribution? For example, suppose through Vikri auctions, we can extract the highest valuation consumer's utility, and then we can further do a optimization and redistribute that value among the agents
yeah.
as we want.
So we can set up an extended game where, in stage one, we ask people their values and allocate to do a Vikri auction and do it. And in stage two, we devise a way to redistribute the gains from the Vikri auction and so on. But remember, for any such extended game, the revelation principle says that there must be a one-shot game where I just ask value and determine payments and allocations. Okay. So even maybe it is possible to set up such an extended game where we do, in stages, some kind of optimization and redistribute and so on. But we are looking at the direct revelation mechanism of that. And essentially, if you have such a mechanism in mind, I can always write down a direct revelation mechanism which does the same thing. Okay. So what I'm going to tell you is basically about the direct revelation mechanism. There might be some alternate implementations where we do this in stages, these redistributions also. Okay. So the primary examples to keep in mind is what's called a bequest allocation problem, where you don't have a will. So if you have a bequest allocation problem, some houses, or a very high valued property is left with a bunch of claimants. Because there is no will, nobody is a clear winner. So a natural way is to basically, realize the maximum possible value from that property. But again, the realized value needs to be redistributed amongst the agents in an incentive compatible way. Okay, so that's basically the kind of application we have in mind. Another application is this land acquisition. So think of a land acquisition where basically, the government has trying to take some land from some farmer, let's say, and trying to give it to someone who has a very high value for that. But then, the value realized from that transaction needs to be redistributed amongst the various farmers or other claimants. Okay, so that these are the kind of examples we have in mind. And of course, as I said, in 2-3 lectures we are going to get into full blown into these models. Right now I just want to give you some preview of some mechanisms that we can think of directly using our results already.
Sir, is it the case that due to this redistribution problem, we are going to have additional constraints on payment rules over and above the DSIC constraints?
Not really. I mean, we are not going to have constraints, but we are going to basically play around with this PI 0t minus I terms, right? So that's the only, remember that is, besides F, the only flexibility that we have is this PI 0t minus I term. So we're going to design our mechanisms through F and PI 0t minus I. Okay, so that we can we can see that we are redistributing more than the traditional Vikri or some other mechanism. Okay, so yeah, I mean, ask this question once we are done with the two examples, essentially. Okay, so first is this simple redistribution mechanism. This is basically a Grove's mechanism. That is, it allocates efficiently. So it'll look exactly like the Vikri auction, in the sense that I will give the object to the highest valued agent. So F is the efficient allocation rule. In the Vickrey auction, Pi 0 T minus I is equal to 0. That's what I'm going to change here. I'm not going to have Pi 0 T minus I is equal to 0. I'm going to define Pi 0 T minus I is equal to minus 1 over n times the second highest in the types of other agents. So second highest in Tj, J not equal to I. Okay, and you'll see why such a choice has been made, and basically it leads to some nice redistribution property. We have you can try other things also, like you can try highest in Tj also and other kinds of choices. I mean, there are many choices we have, but I have chosen one particular formula for Pi 0 T minus I, and I'm going to say tell you that it leads to a good redistribution of the value realized by the highest value agent. Okay, so remember that this allocation rule is efficient. So if if there are n agents, then the highest valued agent realizes his value, and this Pi 0 T minus I choice is a way of redistributing that value. Okay, we'll see how that happens. So because this term Pi 0 T minus I is negative, so basically it says that both winners and losers are compensated some amount. Okay, so losers are obviously compensated this amount, and winners are also, they, you'll see that a winner will pay something and then will be compensated something also. Okay, so such compensations will make sense in a variety of problems, and we have already talked about some applications, but you'll see how it happens here. So just for simplicity, consider a type profile T where there are no ties. I can do all these calculations with ties also, but just that it will be complicated to write down. But think of a type profile where T1 is the unique highest type, then T2 until Tn. Okay. So because this mechanism is efficient, at this type profile, agent 1 wins. Okay. So he's the winner. And according to the formula or the characterization, we know how to compute the payment. Well, its payment is going to be P1T is equal to P1 0 T minus 1. Plus, notice that it's a deterministic mechanism. So in the deterministic mechanism, there is going to be some simplification. As we said that in the deterministic mechanism, P1T will be just P1 0 T minus 1 plus the cutoff point. Well, this is how we determine the cutoff point. So it's T1 minus this integral 0 to T1 F1 x T minus 1 dx. But this cutoff point will then come out to be T2, because T2 is the lowest type at which agent 1 starts winning, right? So it's going to be P1 0 T minus 1 plus T2, which, but what is P1 0 T minus 1? P1 0 T minus 1 is minus 1 over n times the second highest in Tj. Well, second highest in Tj is T3, right? So second highest here is T3. So this is minus 1 over n T3. So it comes out to be T2 minus T3 by n. Okay. So agent 1 pays T2 but is compensated T3 by n. Okay. So that's agent 1. How about other agents? Well, other agents are losers. So remember, for losers, the payment in a deterministic mechanism is just Pi 0 T minus I. So we just use that. So in that case, it's just P2 0 T minus 1, which according to this formula is going to be minus T3 by n. Okay, so if you remove T2, the second highest of that is T3, so it's minus T3 over n. For agent J greater than 2, they are also losers, and for them the second highest would be basically T2, right? So their payments will be minus T2 over N. Okay, so the main takeaway here is that agents 3 through N will get a compensation of T2 by N. Agent 2 gets a compensation of T3 by N, and agent 1 pays T2 minus T3 by N. So the mechanism is slightly, unfair to the second highest agent because her compensation is lower than the compensation of lower valued agents. But let's ignore that aspect of this mechanism for the moment. Okay. So is everyone comfortable with this payment calculations? Any questions?
No.
Okay. So let's look at the total payment collected from this mechanism. Okay. So as I said, this mechanism is efficient. So the payment rule that I constructed basically makes it a Groves mechanism, right? So it satisfies ex post IR because the payments are, the lowest type payments by definition, pi 0 t minus I is less than equal to 0. So it satisfies ex post IR. Okay. And the total sum of payments. Now, if I sum these payments up, so here n minus 2 agents receive this much compensation. So it's minus n minus 2 T2 by n. Agent 2 receives this much and agent 1 pays this much, right? So if you sum these things up, if you sum these three terms, you'll get 2 by n times T2 minus T3. So you should quickly verify that the sum of these payments is exactly equal to 2 by n T2 minus T3. And this is basically obviously a non-negative term because T2 is greater than T3. So the mechanism is feasible. So, basically the mechanism will generate some revenue. It will never ask the designer to make payment. So in that sense, it's a feasible mechanism. More importantly, as n tends, this should be infinity. As n tends to infinity, so as the number of agents become larger, then the sum of payments reach zero. So this term approaches zero for larger and larger number of agents. Okay. So as n tends to infinity, the total payment collected becomes zero. Okay, so this is the distinguishing feature of this mechanism from the Vickrey auction. So what it means is that this mechanism asymptotically redistributes all the surplus that it is getting from the highest value agent. Okay, right? So essentially, it's getting this. Agent one is realizing a value of T1, but it is also making this payment, and this payment is being redistributed to all the agents. And as we sum the total payments, if in an ideal world, the sum of these payments should be equal to zero. What it would mean is that whatever T1 was, we were able to redistribute everything to all the agents. This mechanism is not able to do that. It still generates some amount of revenue, which is 2 by n T2 minus T3. But at least we can say that asymptotically, as n becomes larger and larger, we are able to redistribute everything in this mechanism. And later in later lectures, we will show that basically no DSIC ex post IR mechanism can redistribute everything. The whole T1 can never be redistributed by any efficient DSIC ex post IR mechanism. So in this sense, this mechanism is a good compromise that, okay, we can never distribute everything, but here is an efficient DSIC ex post IR mechanism which is able to achieve the same thing asymptotically. That is, for at least large enough n, we are able to redistribute almost everything.
Very
Okay.
intuitively speaking, why it is so?
Intuitively speaking, why it is so? Well, the payments are designed. Firstly, it is DSIC because the payments are cleverly designed so that the DSIC constraints are met, right? Because all we are changing is PI 0 T minus I terms. And as long as we satisfy this integral formula and F is anyway efficient, we know that this is DSIC. Ex post IR is maintained again by the choice of this PI 0 T minus I, and the reason we are able to redistribute most of it is because we have these payment terms, which is intuitively we are trying to extract uh, as much redistribution as possible, right? So basically here, the uh, ideally we would have liked to take take like to take the highest of TJ, but if you do that, then it so happens that I mean, you should definitely try doing that. Instead of second highest, try to do highest of TJ. So that basically means uh, that these terms that you get don't nicely cancel out, and you don't get that asymptotic term anymore. So you should definitely try to do that. So these all I can say for intuition is that the PI 0 T minus I terms are so cleverly executed so that the terms cancel each other out, and essentially uh, the redistribution amount converges to zero. I mean, the amount of payment that we collect converges to zero. Another way to think about this is that the DSIC constraints are very strong already. Okay, and if you impose additional constraints like efficiency, ex post IR, the set of DSIC mechanisms will become smaller and smaller. If you impose that every surplus that you generate, every value, the maximum value that you generate is perfectly redistributed, then that is too much of a constraint. So that means that there is no such mechanism. This mechanism that we have chosen is just as, and not imposing that constraint all the way, the complete redistribution, but cleverly choosing a payment formula so that the redistribution is done in an asymptotic way. Uh, yeah. So basically, there is a question that if instead of 1 over n, if you do 1 over n square, should that we would we have a better asymptotic convergence? You should definitely try that. My guess is no, because uh, so the reason the 1 over n term is coming because we are kind of you know going to get this n minus 2 term here. So there is going to be a linear term in the numerator. So to be able to cancel that linear term in a nice way, uh, I think it's important to have the or maybe not. Mm, No, I don't think you will get, but you should definitely try all these things. To just to get a better idea of why this 1 over n term is giving you asymptotic. But what happens if you do 1 over n square or 1 over n to the power p? Let's say, okay, what happens to that? My guess is you will run into problems. Okay, so of course, if you're interested to know that what is the best redistribution we can do. Okay, so that is a very, very complicated problem, and best redistribution would involve more complicated terms, and there is definitely no simple expression for that. Okay, so if you're interested, write to me, and I'll point to appropriate papers on that, and we'll
Sir,
discuss
but
some of it in the coming lectures also. Yeah.
what will be the notion of a best redistribution here?
Yeah, what will be the best notion of redistribution? So essentially the idea here will be, okay, so I have not been very formal on this. So what we want is, we want an exposed IR, dominant strategy, incentive compatible, efficient mechanism, which maximizes the sum of utilities of all the agents, right? So you want to give as much utilities, not value, but utilities to the agent. Remember? So, for instance, if you achieve complete redistribution, then the sum of utilities of all the agents will be T1, right? So that's the maximum possible utility agents can, sum of utilities agents can get. So the mechanism. So we know that there is no mechanism which can achieve that. So what we are interested in, finding the best possible redistribution, that is the maximizing the sum of utilities subject to this IC and IR constraints, essentially. Okay, so that's the notion. And here I'm just giving you one feasible solution which seems to be doing well. Okay, and you should definitely try other choices and see what happens. You should try instead of second highest, why not third highest? What about highest? Other kinds of things, 1 over n square, all kinds of things. Okay. But I'm going to tell you another mechanism which has another similar redistribution properties, but it has different choice of f and pi0 essentially. So this mechanism was proposed by Green and Lafont, and it's popularly known as the Green-Lafont redistribution mechanism. One interesting observation here is that this mechanism is not efficient. So it does not give the object to the highest valued agent with probability 1. Okay. In fact, the allocation rule is as follows. It gives the agent to the highest valued agent with probability 1 minus 1 over n, and to the second highest valued agent with probability 1 over n. So to start with, the total surplus or total value realized by this mechanism is no longer T1. It's T1 times 1 minus 1 over n plus T2 by n. Okay, so that's the total value realized by all the agents in this mechanism. In the efficient, if you take any efficient mechanism, the total value realized by all the agents is T1. In this mechanism, because it's not efficient, the total value realized by all the agents is strictly less than T1. Okay. So there is an alternate interpretation of this allocation rule, which was provided by Green Lafont themselves. So their interpretation is that it's a randomization over a bunch of deterministic mechanisms. And so what is this randomization? So essentially the randomization is the following. Choose one agent uniformly at random. So this agent we are going to call a residual claimant agent. For the remaining n minus 1 agents, we are going to do a Vickrey auction. Okay, so remember, Vickrey auction will generate a revenue which is equal to the second highest value. So amongst those n minus 1 agents, it will choose the second highest agent's value to be the payment. That payment is given to this residual claim. Okay, so notice that this once you do the randomization, this deterministic mechanism is incentive compatible, right? Because the residual claimant's type does not matter. So whatever utility he receives only depends on the revenue collected from the n minus 1 agent mechanism. So he has no incentive to lie because his types don't matter. Amongst the n minus 1 agents, we are conducting a Vickrey auction anyway. So that is dominant strategy incentive compatible. So the overall mechanism is incentive compatible. We have already studied earlier that a convex combination of deterministic mechanisms is always a incentive compatible mechanism. Like, so if you take deterministic incentive compatible mechanisms and take a convex combination of that will always generate a dominant strategy incentive compatible mechanism. Hence, this, uniformly choosing a residual claimant with probability 1 over n and doing a victory is a dominant strategy incentive compatible mechanism. Now, observe the allocation rule in this, the allocation probabilities in this mechanism. If I'm the highest valued agent, I get the object with probability 1 minus 1 over n, because the only time I will not get the object is when I am the residual claimant. And I am the residual claimant with probability 1 over n. So the probability with which I don't get the object is 1 over n. Hence, I get the object with probability 1 minus 1 over n. When the highest valued agent is the residual claimant, the object is awarded to the second highest valued agent, because the n minus 1 agents will contain the second highest valued agent. So the second highest valued agent gets the object with probability 1 over n. That's exactly the reduced form rule that I have written here. So here I have just directly written that, the f allocates the probability to the highest valued agent with probability 1 minus 1 over n, and second highest valued with probability 1 over n. But the alternate implementation is through this residual claimant mechanism. Okay, so of course this residual claimant interpretation also specifies the payments, right? Because when when an agent is a residual claimant, he receives the second highest value amongst the other agents. When he is not the residual claimant, he pays an amount equal to the second highest value. So from that you can infer the payment. So I'm going to tell you what the payment looks like by specifying pi 0 t minus I. So pi 0 t minus I is exactly what we had chosen in the earlier mechanism. It's minus 1 over n, second highest in tj. So the way to interpret this 1 over n is this, this probability with which you are becoming a residual claimant. So that's the way to interpret this. And that's why we have this 1 over n term here. And so whenever you are the, you are the residual claimant, you're going to get the second highest of the TJs, and that happens with 1 over n probability. And so basically, even if you're not winning and you are not the residual claimant, basically somehow pi 0 t minus I would be equal to this. Okay, so when you're not the residual claimant, if you're not winning, you pay 0. So that that is anyway 0. But when you're winning and you are not the residual claimant, obviously you're not the residual claimant, in that case you pay an amount equal to T2, right? So that basically happens with certain probabilities, and all this is captured in this pi0 expression. Okay, so let me go over this calculation and we'll see how it all adds up. Okay, so we take the same pi0 term, but important thing to remember here is that the f in this mechanism is very different from the f we used in the earlier mechanism. The f in the earlier mechanism was the efficient one. Here it's not the efficient one, and that will result in different expressions for payment. Okay, so again, look at a type profile like this. Okay, so we know that if agent 1 makes a he wins, then pi 0 t minus I is this is the minus 1 over n times the second highest of tj's. Now we use the payment formula now. So basically the payment formula is essentially right? So this is the payment formula. So Ti times the probability of winning. So T1 times the probability of winning is 1 minus 1 over n, minus this integral. Well, when does he or she wins? Well, so that expression is a little complicated here, because in the interval T2 to T3, he wins with probability 1 over n. Okay, so that's why that integral is 1 over n t2 minus t3 in that interval. And then from t1 to t2, he wins with probability 1 minus 1 over n. Okay, so I'm just simplifying this integral expression here, right? So this integral expression will be 0 below t2, will be 0 below t3. Between t3 to t2, it will win with probability 1 over n, and above t2, it will win with probability 1 minus 1 over n. So if you plug those things in, then this integral expression will simplify, and we'll get a term like this: 1 minus 2 by n times t2. So again, if you think about the Green-Love residual claimant interpretation, you see that with 1 minus 1 over n probability, he makes a payment equal to t2. But with probability 1 over n, he's compensated t2, right? Is that clear? Right. So basically, the term comes out to be 1 minus 2 by n times t2. Okay, so and agent 2 makes a payment equal to 0 here, because again he's compensated minus 1 over n t3. Okay, and if you evaluate that expression, basically between so he gets the object with probability 1 over n, so this is t2 by n, minus that integral, he gets the object only between t2 and t3 with probability 1 over n, so this is this, and that evaluates to 0. Again, if you look at the residual claimant interpretation, with probability 1 over n, he is the residual claimant, and in that case he receives a payment equal to T3 over N. That's correct, right? Yeah, he receives the object with probability. I mean, in that case, his residual, his compensation is T3 over N. But when he's the winner, the residual claimant has to be the agent 1. So he makes a payment equal to T3, and that happens with probability 1 over N also. So both the winning payment and the compensation cancel each other out. So agent 2 makes an aggregate expected payment of 0. All the other agents, get a compensation equal to minus 1 over n t2. Okay. And again, that basically follows because they only, receive payment when they are the residual claimant. And that happens with probability 1 over n. And in that time they receive a payment equal to t2. So the expected payment they receive is just t2 over n. Okay, and so using our formula also, you get the same expression. Okay, so the total payment collected, if you sum this up, not surprisingly that this sum is equal to 0, and that follows because each of those deterministic mechanisms, remember, was totally budget balanced. Whatever we were collecting from the n-1 agents, we were giving to agent the residual claimant. So each of them were budget balanced, so their convex combination is also budget balanced. So the total payment collected from this mechanism is 0. Okay, so in this sense, even though the allocation probabilities are not efficient, whatever surplus or whatever value is realized by this mechanism is completely redistributed in this. In the earlier mechanism, we were maximizing our value that we could realize, but we were not able to redistribute. Here, we are not able to completely achieve the maximum possible value, but we are able to redistribute everything that we are able to achieve, right? So it's a budget balanced mechanism. Okay. So it's not a gross mechanism because it's not efficient, but redistribute surplus completely. Remember, the surplus generated by this mechanism is, agent 1 gets the object with this probability, and agent 2 gets the object with this probability. So this is the total surplus achieved by the mechanism, T1 minus 1 over n, T1 minus T2. And again, as you see that when n tends to infinity, this expression actually tends to T1. So in some sense, this mechanism also asymptotically redistributes all possible surplus. Okay. But the nature of distribution in both the mechanisms is quite different. So in the first mechanism, we had an efficient gross mechanism, and but it was a feasible mechanism where money was left on the table, and you can say that that money needed to be bought. So basically, uh, we didn't know how to, everything that you cannot redistribute is something which needs to be bought, because if you distribute by some ad hoc manner, we will destroy either incentive or participation constraint. So any money left on the table, unless the seller is taking it away, and if it is not being able to redistribute amongst the agents themselves, then it is basically burned. Okay. So in the first mechanism, we maximized our value, but we could not redistribute everything. In the second mechanism, it was a non-gross, inefficient, but budget balance mechanism. Inefficiency basically prevented maximum redistribution in this case.
Sir, suppose in the first case the left out money is distributed equally, so
Yeah.
the constraint which we will violate is DSIC precisely.
Incentive compatibility. Yeah. Yeah. Some agents will have, incentive to say that I'm not the highest agent, but I'm the second highest or something, because then he will get back more money than what he's paying. I mean, basically, what utility he is getting. Okay.
Okay.
You should check all these things. You know. Okay, so these are two examples that I wanted to give. So just to give you a flavor of how you can use these DSIC characterizations to give, construct particular mechanisms. So in the first case, we just played with PI zero terms to construct a mechanism which can redistribute a lot of surplus. In the second case, we simultaneously played with F and PI zero. So we chose an F like this, and then constructed this PI zero so that the budget is totally balanced. So this choice of F and P made it a budget balanced and incentive compatible, dominant strategy incentive compatible, ex post IR mechanism. And but it is not efficient. So what we are going to do is now look at, uh, I'm going to quickly look at what happens if we weaken incentive compatibility. But before I do that, any questions on this part of the analysis so far? Any broad questions? Okay, so as I said, please look back at the videos and let me know if you have questions. So what we're going to do is now look at the consequence of weakening incentive compatibility. As we know in game theory, there are two prominent strands of equilibrium. One is the dominant strategy equilibrium, which is a very demanding requirement that irrespective of what other agents are using a strategy, your strategy must be dominant. Okay, so you have a dominant strategy to play in the mechanism. And the weaker notion is what is called the Beige-Nash equilibrium, where basically It's the generalization of Nash equilibrium to Bayesian games, where you say that if others are following a particular strategy, then my expected utility is maximized by following a particular strategy, right? So that's basically the Bayesian equilibrium. And so what we're going to see here is that in the single object allocation mechanism, what is the modification of our characterization if we use Bayesian incentive compatibility as a solution concept rather than dominant strategy? And one of the reasons we look at Bayesian incentive compatibility is that a very, very widely used mechanism, namely the first price auction, is Bayesian incentive compatible, but not dominant strategy incentive compatible. And if you remember, in game theory 1, we had shown that the first price auction under symmetric assumptions has a unique symmetric Bayes-Nash equilibrium. Okay? And basically what it means is that when we look at the direct revelation mechanism of that direct revelation mechanism will have a equilibrium where agents would truthfully report their type. And truthfully reporting their type is a Bayesian equilibrium of that direct revelation mechanism. Okay? So then it basically asks the question that you can ask the question that then what are the class of all Bayesian incentive compatible mechanisms? Are are there other kinds of mechanisms that we are missing out that we should be looking at, and or is everything like first price auction or something like that? Okay, how are they different from dominant strategy incentive compatible mechanisms? Okay, so that's basically the reason we look at Bayesian incentive compatibility. And so because it's a Bayesian incentive compatible solution concept, so we know that to define Bayesian games, we need to assume some priors over the type space and so on. So in particular here, we're going to assume that there is a common prior G on the set of type profiles Tn with a positive density G, small g. Okay. So that what it means is that the sequence of events is as follows. Nature draws types using this capital G and informs every agent its own type, Ti. So agent I knows his type Ti. So because this G is common knowledge, having observed your own type, you have a conditional distribution over the types of other agents. Okay, so that's basically denoted by GI, this particular function. So GI conditional on TI is the conditional distribution of agent I over the types of n minus I. Okay, and it has a density small gi. Okay, so I mean, these details are not so important. I mean, we are going to abstract away from all these calculations and so on, so you don't have to worry about what is the expression of all this and so on. Don't have to worry about all this. So the main idea is once I observe my type, I have a belief about what is the probability with which other agents might have received their types, and that's basically specified by this GI function. Okay, so each individual believes. So to define this Bayesian incentive compatibility notions, everything has to be computed in an interim sense. So what I mean by interim sense, once I observe my type Ti, I need to take action in this game, in this Bayesian game. So I need to decide in this mechanism what type I will report to the mechanism. And then because I'm evaluating everything at this stage, I'm going to take expectations over the other agents. And that basically gives rise to this interim term. Okay, so here is the first expression. If you understand this, everything will be clear. Suppose I am agent I and my true type is Ti, and I'm contemplating whether I should report some type Si to the mechanism. Okay, so remember it's a direct revelation mechanism. So the only message that you can send to the game is basically your, a type. Okay, so that's the message space is your type space. So what is the interim allocation probability of agent I, whose true type is Ti, and he is deciding to choose Si to report? Well, if he reports Si and others have T minus I as their type, remember the solution concept is that if others decide to report T minus I truthfully, what is my expected utility maximizing strategy, right? So in this case here also, if others report T minus I, I'm assuming that others are reporting their true types. And hence, the probability with which this event will occur is small g T minus I given my type is Ti. So this is the probability with which others have type T minus I if I have Ti. And hence, with this probability, I will get Fi Si T minus I as my allocation probability. I am reporting Si, my reporting type, but this this probability is computed with respect to true type, right? Because true type has nothing to do with this probability that others have type T minus I will depend on your true type, but not on the type that you're reporting, right? Because nature is deciding that. So this is, you integrate over all T minus I, it will give you the allocation probability of agent I when his true type is Ti, but he reports Si. So this is what we will call the interim allocation probability of agent I. Notice that if types are independent, that is each agent I is drawing his, nature is giving each agent his type independent of other types, then this conditioning is, irrelevant. We don't need to do such conditioning. So this term becomes independent of Ti. This whole expression becomes independent of Ti. Independent of what your Ti is, the G of T minus I is the same. And this expression was anyway independent of Ti. So the whole interim allocation probability is independent of Ti. Okay. So the conditioning is only relevant if there is correlation across agents about the types. Okay. Similarly, you can do an interim payment computation. So the interim payment of this agent is computed similarly. This is the payment you make if you report Si and others report T minus I. Remember, others are reporting truthfully. So this is the probability with which others will report T minus I. So hence, this is the expected payment you will make in the mechanism. Okay. So using these two notions, we can compute what is the utility of an agent I if his true type is Ti and he reports Si to the mechanism. Well, this is the expected value he will get. Ti is his true type, and this is the probability with which he will get the object, minus this is the expected payment he will make. So this is the expected utility of the agent who has type Ti but reports Si. Okay. So Bayesian incentive compatibility says that this utility is maximized for Si equal to Ti. So for all possible Si's, I can compute this expression and the maximum of those will occur at Ti. That's exactly Bayesian incentive compatibility. A mechanism FP is Bayesian incentive compatible if for every I and every Si Ti, an agent with type Ti prefers reporting his true type to any other type Si. Okay, that's the Bayesian incentive compatibility constraint. And if you disentangle this UI term, it basically says that this interim utility is greater than the lying interim utility. Okay, so truth telling maximizes interim utility given that others report truthfully. Okay, that's basically it. In other words, truth telling strategy is a Bayes-Nash equilibrium of the induced Bayesian. Any questions? Great. We are following it. Uh, so I'm going to stop in 5 minutes. So just give me 5 more minutes. So of course, as I have already said, that with independent priors, all these expressions become, independent of this conditioning. So we can just drop these conditioning ti terms, right? Because these become, we don't need to condition it anymore. So throughout these lectures now, I'm going to assume that this prior is independent, so there is no correlation across the agents. So essentially what I'm going to assume is that each agent draws its type independently. In particular, agent I draws its type from 0 pi using distribution small gi with positive density, capital Gi with positive density small gi. Okay. So the alpha Si and pi Si can now be written without the conditioning terms. That's what I'm saying. Okay. So this pi Si, which is the expected or the interim payment, is no longer needs to be conditioned, and this alpha Si also doesn't need to be conditioned. So the incentive compatibility constraint, you can rewrite using the same way, that for every I, for every SI Ti alpha I Ti minus pi I Ti is greater than equal to Ti alpha I Si minus pi I Si. Okay. Do a similar algebraic manipulation that we did for DSIC. On the right hand side here, add Si alpha Si and subtract Si alpha Si. This particular term is your UISI, okay, and you're left with this. And so the incentive constraint is now UITI is greater than equal to UISI plus TI minus SI alpha SI. So it looks exactly like the earlier constraint, except that now these are in interim terms. So earlier it was all in terms of exposed terms. Now it's in interim terms. Okay, and you can easily see that alpha is now your subgradient map of UI. So basically, immediately you can write down an analogous characterization of Bayesian incentive compatible mechanism. So what you have is instead of non-decreasing exposed, you have non-decreasing in expectation. So what it means is that if you take two types of agent I, Si greater than Ti, then the interim allocation probability at Si is greater than equal to the interim allocation probability at Ti. Okay, so this is the allocation rule property. So the characterization will say that FP is Bayesian incentive compatible if and only if F is non-decreasing in expectation, and for every I and every Ti, Ui Ti equal to Ui 0 plus 0 to Ti alpha x dx. So the subtle change here is that there is no T minus I quantifier here. So that has been integrated out essentially. And you have BIC equivalent to non-decreasing in expectation and this payoff equivalence formula. Okay, so that's the characterization, and proof is identical almost to DSIC case. And just like in the DSIC case, you can write down a payment version of this by just expanding this UI formula. If you expand it, it becomes pi I Ti equal to pi I 0 plus Ti alpha Ti minus this integral. Okay, so you can write down this revenue equivalence now easily, that pi I Ti minus, if you have two mechanisms, FP and FP prime, so they have the same allocation rule, but the payments P and P prime might be different. But if they are different, then because of BIC, they can only differ in the following manner, that pi I Ti minus pi prime I Ti is equal to pi I 0 minus pi I prime 0. What it means is that if there are two mechanisms whose interim payment of the lowest type is the same, that is pi I 0 equal to pi I prime 0, then the interim payment at every time is the same. Okay, the mechanisms might be different. P and P prime might be different potentially, but the interim payments are the same. The expected payments of a type is the same if the expected payments of the lowest type is the same. This is what is known as the revenue equivalence in standard auctions. So remember, in a symmetric first price auction, there is a unique symmetric equilibrium where the highest valued agent wins. So symmetric means that all the distributions of the agent, so each agent is drawing from the same support using the same distribution. In that case, first price auction has a unique symmetric equilibrium where the highest valued agent wins. We know that in second price auction also, the highest valued agent wins in a dominant strategy equilibrium. So what this is saying is that when bidders are symmetric, the allocation rules in both the mechanisms are the same. So that's what this revenue equivalence is also hinting, that the F is the same. So that's what we are observing in first price and second price auction. In Bayes-Nash equilibrium of both the games, the allocation rule is the same. Now all we need to make sure is that the interim payment of the lowest type is the same. And that is indeed the case in both the auctions, first price and second price. If your type is 0, you pay 0. Hence, in expectation also, your expected payment will be 0. But then immediately what this means is that this term is 0, and hence these are also must be equal at every time. So it means that by revenue equivalence, expected payment in both the auctions must be the same. Okay. So without doing all these, calculations of computing the revenue, expected revenue from first price and second price, we are able to conclude that the expected revenue from first price and second price must be the same, because the payment at the lowest type is the same, which is 0, and the allocation rule is the same. So of course, this is not restricted to only the first price and second price auction. It is true for any standard auction. So standard auction is an auction where highest valued agent wins and the interim payment of the lowest type is 0. This is the feature in many auctions, and many auctions have such equilibrium. And so revenue equivalence will imply that the expected payment across all these auctions must be the same. And the driving feature which implies this result is that the allocation rule in equilibrium of these auctions is the same, and the interim payment of the lowest type is the same. That is basically driving all these results. Okay, so if you remember this, I mean, this is the key takeaway from this lecture. And just to conclude, yeah, I mean, this
So
part,
the exposed payments may be different, but
exposed payments may be different. So state by state, I mean, which is true in victory and first price also, at every type profile, the payments might look very different, but the interim payments of a type is the same. Okay, so the expected payments would be the same. Yeah. Okay, so let me just conclude quickly by telling you about the interim participation constraint. So earlier in the lecture, I told you about exposed participation constraint, and that was equivalent to pi 0 t minus I is less than equal to 0. And here you can do the same thing, and here the constraint, the condition will be pi I 0 is less than equal to 0. So the interim payment of the lowest type is less than equal to 0. Maybe I should read out the interim individual rationality constraint, what it says. So a mechanism FP satisfies interim individual rationality if for every I and every TI, its interim utility is greater than equal to 0. Okay? Because the interim utility is greater than equal to 0 requirement, the analogous if and only if condition is that the interim payment of the lowest type is less than equal to 0. Okay, so pi I 0 has to be less than equal to 0. And the proof is again the same proof. Okay. So what we have done is we have looked at dominant strategy and DIC characterizations using this convex analysis techniques. And we have also looked at the interim and ex post participation constraints and how we can leverage our characterization to give if and only if conditions for those participation constraints also. So it seems like one of the things is that the BIC conditions are monotonicity of interim allocation probability and an interim revenue equivalence formula. DSIC is monotonicity of ex post allocation probability and ex post revenue equivalence formula. So here is an example to show that the two the VIC mechanisms are, need not be DIC. I mean, we already know that from first price auction, but this is a simple example to show that, uh, you know, uh, expected monotonicity would not necessarily imply ex post monotonicity. So here I have a type space 0 to 1 for each of the agents. So type of agent 1 is on x-axis, type of agent 2 is on y-axis, and I have divided this into smaller cells, with 1 by 5, 2 by 5, 3 by 5, 4 by 5, like that. And basically these numbers in these cells represent the cells where agent 1 is winning. So here, these are the places where agent 1 is winning with probability 1. In all other cells, agent 1 is winning with probability 0. We don't need to worry about where agent 2 is winning. I want to point out here is that this particular allocation rule is not non-decreasing, because look at here and look at this particular type of agent 2. As we increase agent 1's type, we encounter 1 once and then 0 again. So it's non-monotone in this region, right? So agent 1's allocation probability is decreasing in this region. Okay, and then it increases again. Okay, so it is, and here also it's 1 here and 0 here. So as agent 1 increases its type for a given type of agent 2, the allocation rule is decreasing. Okay, but I want to claim that this allocation rule is indeed non-decreasing in expectation if you assume that the prior is uniform. So if all the types are occurring with the same probability, then the expected allocation probability of this agent is non-decreasing. Why? Look at any agent in these two type of agent 1 in these two cells. The expected allocation probability is 0 because it does not win the object in any of these vertical axis, right? So here it's 0, so the expected allocation probability is 0. Here it's 1 by 5 because this is the only cell where he will win, and this cell has 1 by 5 probability. So here for any type in this interval, the expected allocation probability is 1 by 5. Here it's 2 by 5 and here it's 3 by 5. So the expected allocation probability is indeed non-decreasing, but it's not an exposed non-decreasing rule. But notice one thing, that we can always convert such a rule to a non-decreasing allocation rule. All we need to do in this example, at least, basically bring this down, this one here, and this one here. You'll see that the resulting allocation rule, this is a new allocation rule, which will be non-decreasing exposed. Okay. And moreover, the interim allocation probabilities of every type remains the same. So it's 0, 0, 1 by 5 here also, because we only moved it down, 2 by 5 here and 3 by 5. So it seems like, even though BIC seems like a weaker condition, there is a quote unquote equivalent DSIC mechanism which can achieve the same interim allocation probabilities. Okay. I mean, this is just a
Sir, but we need to take care of agent 2 also if we move
agent 2
one step.
also. So that's the trick. So here I'm just doing it for agent 1. So what Manelli and Vincent showed that you can do it for n agents also. Okay, so we need to here. I haven't told you anything about agent 2, but there is a way of doing it such that agent 2's monotonicity is also maintained. Okay, and that's what Manelli and Vincent showed in a remarkable result, which was unproved for like quite a few years and only proved recently. They showed that if you have a mechanism which is Bayesian incentive compatible, there exists another mechanism, and that mechanism can be very different, F prime P prime, but it will be a DSIC mechanism. And importantly, the interim allocation probabilities of each agent and interim payments of each agents across these two mechanisms is the same. So it looks like, at least for single object allocation problems, where types are drawn independently, the BIC mechanisms is not really a bigger class than DIC mechanism. It may be, exposed, it may look very different, but interim, it is the same. And if you think about it, that's what's happening in first price and second price auction. Even though we have a first price auction, which is a Bayesian incentive compatible, which is Bayesian incentive compatible, we can always construct this second price auction, which has the same interim terms, but that result is true even more generally. So it's not restricted to second price and first price, but you take any arbitrary BIC mechanism, you can construct a DIC mechanism which is equivalent. Okay, so I'm stopping here unless there are some questions. Any questions?
So can you share these slides?
Yeah, I will share it right away. It will be uploaded on the course website also, and I'll also send an email. Okay, sorry I took slightly longer than usual. Maybe I'll take a smaller class, a shorter class in the next class. Okay, so please keep reading the notes. And another thing, I will send you an assignment which you can work on also simultaneously. Okay.
Okay, sir.
Yes, sir.
Okay. Thank you.
Thank you,